Good day, everyone. My name is James Frimpong, and this is my 10th project presentation for our Advanced Mine Design course. So today I'll be presenting on the geomechanical characterization of backfill. So in mining, once we take the valuable ore out of the ground, we are left with some empty spaces in the ground that we call voids, and we can't just leave them empty because the ground might collapse. So we fill them. The spaces that are left after we extract the ore, we fill that space with the material that we call backfill. And so this is the material that I'm going to talk about. My presentation isn't just about how we fill them, it's about understanding the mechanics of the material. We need to know if the material is strong enough, if it will flow like a liquid or it will stand like a solid, and most importantly, how does this material interact with the rock walls around it, just so we can make sure that mining activities are kept safe. This will be the outline of today's presentation. First, we will give some brief background of this material. So we are going to learn about why this material exists. We will talk about the types of backfill we have. We will also look at the geomechanical framework. We look at some key material properties. We look at laboratory and in situ characterization of this material. We also look at some failure mechanism and stability concept. And then we will be looking at design implications and also some current challenges and research gaps in this field. Let's start with the basis. What is mine backfill? So as I said in the introduction slide, it's a material that we place underground to fill the voids that we create after we extract valuable minerals from the earth. And we don't do this for fun. The reason why we do this is because of some specific engineering objectives. And the first is ground stabilization. This is purely safety reason. So when we remove the ore, the rock walls wants to collapse. And so we put this material back into the space that has been created. And this material creates some confinement so that the surrounding rock does not fall. The second is to provide a working platform. So there is a mining method that we call cut and fill. And with this mining method, the miners actually drive their heavy machinery on top of the backfill to reach the next level of ore. So the backfill material must be strong enough just so the machinery can operate on the backfill. And finally, waste disposal. So mines produce massive amounts of waste tailings. So instead of storing them in tailings dams on the surface, and which can fill or even leak into surrounding water bodies, we use this material as structural support underground. So in that case, we don't have to waste money to construct tailings dams. We don't have to worry about the tailings seeping into nearby groundwater bodies. And so we are basically reusing the waste material as a support system underground. So now that we know what backfill is, let's see exactly where it fits in the mining world. So we classify underground mining methods based on how we support the rock mass. So if you look at the diagram on the right, you can see the three main families of mining. Now on the far left, we have naturally supported methods like the room and pillar. Here the rock supports itself because we leave pillars of ore behind. Now on the far right, we have unsupported methods like block caving. Here we actually want the ground to collapse. That's how the mining method is designed. But our focus is strictly on the middle group, that's the artificially supported stopes. So in these methods, we take out all the ore, so there are no natural pillars left and we don't want the ground to cave in, so we must provide artificial support to hold the wall up. And the artificial support is what we call the backfill material. So specifically, backfill is critical in mining methods like the cut and fill and the long hole open stoping. And backfill isn't just a waste material, it's a structural component that allows us to mine safely. So what is this backfill material? We have different kinds of backfill. So we have paste fill, we have hydraulic fill, we have aggregate fill, and we have rock fill. And the major difference between them is the particle size. And so if you look at the table here, so for the paste fill and the hydraulic fill, they both have tailings, cement, and water, even though the compositions may be different. For the aggregate fill, it doesn't involve tailings because the tailings are too fine. And so it has coarse aggregate, 10 to 40 millimeter diameter, and then it also has some sand, cement, and some water. For the rock fill, it's made up of waste rock, which is less than 2 mm to 300 mm diameter. So the main difference between them is the particle size of each of them. So on the right here, we have a graph here, and this is a particle size distribution. And this graph would tell you what kind of backfill you are dealing with based on the particle size distribution of the tailings you are working with. And so generally speaking, if the particle size distribution of your tailings falls in the coarse region, that means that tailings is suitable for hydraulic fill, but not suitable for paste fill. And if the particle size distribution curve of the tailings falls in the medium region, it means that it's suitable for paste fill and it requires desliming to be used for hydraulic fill. Desliming means we are basically removing extra fines like clays and silt from the tailings. That's what desliming means. So if the PSD falls in the medium region, that means it's good for paste fill, but for it to be used as hydraulic fill, we need to remove some fines from it. And if the PSD falls in the fines region, it means that it is not suitable for hydraulic fill and it requires desliming for it to be used as paste fill. So why does the specific type of backfill matter to a mining engineer or a geotechnical engineer? Why can't we just treat all of them the same? Well, the answer is that the physics change depending on the material. So on top of the list, we have drainage. Some of the backfill let water pass through instantly, whilst others trap it. And so it's good to know what material you are dealing with, just so you can know how water passes through it. Also, we have the cementation. So adding binder changes how the stress moves through the material. And also the mechanical response, which is the behavior can range from a loose soil to a hard rock. So why paste fill unique? Why is it unique? Now paste fill is special because it has high fine content. Remember the particle size curve we looked at earlier? So those fine particles make the material hold on to water. And so water cannot easily penetrate. Yeah, so that means that paste fill doesn't act like solid concrete and it doesn't quite act like loose soil either. It's kind of in between soil and rock. So it behaves as a cemented soil. It's like a hybrid material. Yeah. So this unique behavior is exactly why we need to characterize the process just so we will know how to deal with it. We don't deal with it as a rock because it's not a rock, and we don't deal with it as a sand because it's not a sand. It's kind of in between. So it needs its own characterization method. And so that is what we are looking at. So now that we understand the material types, let's look at the entire life cycle of the backfill. I mean, from how the material is created on the surface to how it ends up underground. So if you look at the diagram on the left, this is the paste backfill plant. It's like a factory. So it starts with the tailings coming from the mill. So we have tailings from the flotation circuits, that's from the mill. And that's where everything starts from. And we run them through thickness and filters. And the reason is to remove excess water from the tailings coming from the mill. And once we pass through that stage, finally it goes into the mixer. And in the mixer, we add binder, and the binder is usually cement or some slag. And so we add the cement, the binder to the tailings, and we add water just so we could create the final paste. So once the mix is done, the paste is pumped underground into the stove. And so that brings us to the picture on the right. And so in this picture, we see the paste being discharged into the void created after ore has been extracted. And at the bottom, we see a barricade. We will talk about this in the next few slides. But the main purpose of the barricade is to create a retaining wall, and that is going to hold the liquid paste in place for as a kiosk, because it contains binder. So the barricade is just providing some support just so the material can cure. Let's ignore the arrows for now. We will talk about the stresses in the next few slides as well. So basically, as the fill cures, it bonds with the rock walls, and so once it bonds with the rock walls, it helps support the weight of the fill, and it also helps to reduce the pressure on the bottom of the barricade, and this is what is going to make the paste fill stand. And once it could stand on its own, mining activities can continue. So this flowchart represents the roadmap for studying this backfill material. It just breaks down the characterization process into 4 logical phases. So phase 1 on the far right is the input material. So before we can design anything, we need to know what we are working with. And so this involves the particle size of the tailings. It also involves choosing the right binder and also checking the water chemistry. And so these 3 ingredients come together to form our mix design. Now, once we have the mix, we move to phase 2, which is the laboratory behavior. This is where we do our standard testing. We look at how the material flows. We look at how strong it gets, as in the mechanical properties, and also how it settles, as in how it consolidates. And this gives us our baseline data. But the lab data isn't enough. We must consider phase 3, which is in situ complexity. So underground conditions are different from laboratory conditions. In underground, we have different elevated temperatures. There are massive scales and the interaction with rock walls that introduces stresses to the backfill. But in the laboratory setup, we may or may not have stresses depending on the kind of test we do in the lab. Yeah. So this third phase is just adjust our laboratory numbers just so we could match the reality. And finally, we have phase 4, that is the engineering design. We use the adjusted data to calculate the stability just so we ensure that the backfill, it doesn't collapse. And also for the barricade design, which is meant to provide support for the backfill kiosk. And so the ultimate goal of this entire process is shown in the final box here, which is safe mining. So everything in each phase comes to this point, which is safe mining cycle. So the main point of the backfill is to ensure safety and make sure that productivity is continued. So this brings us to the core challenge of backfill engineering. So the problem is that backfill has kind of a split personality. It has to do 2 opposite things at different times. First, during transport, it must behave like a fluid. So it needs to flow through mine pipes. So we pump the backfill material through pipes underground. And whilst we are pumping it, it needs to behave like a fluid and it doesn't have to clog. But once you pump it and it settles in the stove, it must behave like a solid. That means it needs to be strong enough to hold up the massive weight of the rock walls. Yeah, so managing this transition from fluid to solid is where things get dangerous. So we divide the risk into 2 time periods. The first is the early age concern. So this is where the fill is still wet. So if you look at the photo on the right, especially the image 1A, image A, yeah, you can see the paste flowing like a lava. At this stage, the paste is very heavy and is very wet. And so the risk here is called liquefaction, which we will talk about in the next slides. So if we shake this wet mud, maybe from a nearby blast, it can lose all its self-weight and flow like water. And this is going to create massive pressure on the barricade, which we talked about, and it can cause them to flood the mine. The second is the long-term concerns, which is after the fill has cured and hardened. Here we worry about the self-standing ability. So eventually we will mine the rock right next to the fill. And so we need to make sure that when we blast that rock away, the backfill will be exposed. And so we need to make sure that the backfill is strong enough to stand vertically without crumbling. We also need something we call stress transfer or the arching effect, which we will also talk about in the next few slides. So we want the fill to actively push back against the wall, the rock walls, just to keep the mine stable. In the next few slides, we will be talking about stress development, consolidation, and pore pressure evolution. Well, now let's look at the stresses or the forces inside the stope. So there are two main type of stress we need to calculate, and you can see them labeled in the diagram. Yeah, so first we have the vertical stresses, the sigma V fill, which is shown by the large downward arrows, the bottom right here. And this is generated by the self-weight of the material. It's simply gravity pulling the heavy paste down. So it's as a result of the self-weight of the backfill itself. And second, we have the horizontal stress, which is the sigma H fill. And that is shown by the sideways arrows that we see right here. Okay, so the sigma H fill, it develops because of confinement. So as the paste tries to settle and squash down, it wants to expand sideways, but it can't because the hard rock walls are in the way. And so that resistance creates the horizontal pressure. It's good to note that the stress distribution is non-hydrostatic. And so if the stope were filled with water, the pressure would be equal in all directions, but backfill acts like a solid. And so the horizontal push is typically less than the vertical weight. And this ratio, as in how much the vertical load turns into horizontal push, it isn't random. It depends on these three factors that I have noted here. So the first is the stope geometry. So the narrower stopes grip the fill better. And we also have the fill stiffness, which is how rigid the material is, and also the degree of cementation. And so all the cement, as the cement cures, the material becomes self-supporting. And so this changes how it pushes against the walls. Now we move to a unique property called chemical shrinkage. And this chemical shrinkage, it helps explain why the paste fill gets so strong even when it's sealed underground. So we often think cement hardens because it dries out, but underground there is no air to dry it. Instead, the cement chemically consumes water through a process that we call hydration. So when the cement gets into contact with the water, a process called hydration occurs. And in that process, it releases the hydration products, which are the calcium silicate hydrates. And these hydration products, it's what causes the cement or the paste to harden over time. So if you look at the diagram on the right, this is the experiment we use to measure the chemical shrinkage of materials. So we place the paste in a sealed vial at the bottom, and we place the paste at the bottom, and we fill the rest with water, and we put a thin capillary tube. This is the tube on top. So as the cement hydrates, it sucks water down from the tube, and we can watch the water level drop day by day. Now, this matters because inside the stove, there is no extra water to suck in. So instead, it creates a negative pore pressure or suction inside the material because there is no extra water. And this suction basically acts like a vacuum seal. So it pulls the particles tightly together. So in geotechnical terms, this increases the effective stress and that's what we call apparent cohesion. So the apparent cohesion is basically the additional shear strength that the backfill gained from the metric suction, which is the negative pore water pressure. And as I explained earlier, the cement hydration consumes the water, and since the backfill is sealed in the stove, the consumption just creates a vacuum or a suction and inside the pore pressure because air cannot easily get out of the fill. And so this suction just pulls the tailings particles tightly together, and according to the principles of effective stress, this creates the friction between particles. So following the chemical changes, we also have the physical process called consolidation. So in simple terms, consolidation is just the material settling under its own weight. And so what happens is that the heavy solids in the backfill is settled to the bottom and it squeezes the water out through the pores. And so if you look at the graph, the graph on the left, that is type 2 dissipation curve. It has pore pressure on the y-axis against time on the x-axis. So this shows the ideal scenario. So the pressure starts high when we pour and then steadily drops as the water drains out, like that. But on the right hand side, that's the type 3. This is a more complex reality. So sometimes the pressure actually rises at first. That's why we see this increase in pore pressure. And then it will start to drop. And this can happen if we fill the stove too fast. And when I say fast, I mean faster than the water can escape. And so this is very critical because of the effective stress principles. And so strength comes from the solid paste touching each other. And so if the water pressure is high, it pushes the particles apart, and that will make the fill weak. And so we need that pressure to dissipate to achieve full strength. If the pressure stays high, then liquefaction can happen, which we will talk about in the next few slides. So this is the ideal solution, the ideal reality, I mean. So when we pour the paste, I mean, the pore pressure is initially high. And as time goes on, the pore pressure dries because the cement is reacting with the water. And so the paste is losing water. And so pore pressure keep decreasing. So that brings us to one of the most important equations in geotech engineering, and that is the effective stress principle, which is given by the effective stress equal to the total stress minus the pore water pressure. The total stress is basically the total weight of the backfill pushing down, and the pore water is the pressure of the water. And so if you take the pore water from the weight of the backfill pushing downwards, you get the effective stress. Now, the strength of the backfill depends on the effective stress. And since the total stress is mostly fixed by gravity, the only way to gain strength is to reduce the pore water. So if you look at the graph on the right side here, the bottom line with circles, that's the water pressure. And you notice how it rises at first during filling. And it starts to drop. Now this drop is very important because in paste fill, the water isn't just draining away. It's being consumed by the cement to form hydration products that I talked about earlier. And so the drop in the pore water pressure is indicative that the cement is hydrating with the water, and it's forming hydration product, and that is what is making the backfill stronger. Now, the last bullet point here highlights a very important risk. So during the early filling stage, the paste is undrained, and so the effective stress is zero. And so what that means is that water is carrying all the weight. And so at that time, the load on the barricade is hydrostatic. And so if the barricade fails at this point, the water will just flow like water. And let's look at some key properties of backfill. And the first is the particle size distribution. And as I mentioned in the previous slides, the paste fill is defined by the proportion of fines. And these particles are what reduces the permeability and traps the water. And so they basically control how packed the backfill gets and how tightly the grains fit together. The second one is the solids and the water content, and this is a very sensitive variable because in paste fill, small change it can create large mechanical effects, and so adding just a little too much water, it can destroy your yield stress and make the material flow too fast, and so it's a very delicate balance here. The third one is the binder type and the type and then the content. So the binder is basically more like our glue. So when we use cement, it provides cohesion and stiffness. And as you would expect, more cement means higher strength, but it also changes how the stress is transformed to the rock walls. And in backfill, majority of the expenditure goes into cement. And so determining the right amount of cement to use for a backfill application is very critical, because the fact that more cement means more strength doesn't mean you go with the highest binder available. No, because you need to optimize some parameters, and the binder content is one of them. And the last one, we have the density, permeability, and void ratio, and they control the risk. So the void ratio is simply the measure of the empty spaces in the mix. And so if the void ratio is too high, the material is prone to liquefaction. And we want a dense material. We want a tightly packed material. And so we want the void ratio to be low. Now let's move on to some mechanical characterization. So there are two critical concepts to keep in mind here. First is the stability. Stability is the difference between a safe mine and a collapse. And the second one is the evolution. You need to understand that these properties are not static. They evolve with curing time because of the cement content. Yeah. And so a sample tested at 7 days behaved completely differently than that sample tested at maybe 14 or 28 days. So to capture the mechanical strength of backfill, usually we rely on laboratory tests, because in situ tests, like the coring, it doesn't really give intact cores because of the low strength of the backfill material. Yeah, so if you try to core through the already placed backfill, it usually results in broken pieces, and you cannot take any geotechnical data from that. So usually backfill experts they do laboratory tests to characterize the strength. And with the laboratory tests, usually they go with the UCS, tensile strength, triaxial stiffness, and deformation behavior. We're moving on to the failure modes of mine backfill, and with that, we will start with the liquefaction of backfill. So now we have arrived at a very critical risk in backfill engineering, which is liquefaction. So in simple terms, liquefaction is when a solid material suddenly loses all its strength and behaves like a liquid. And so to understand the mechanism why this liquefaction happens, we go back to the effective stress rule. So remember that strength comes from particles touching each other. But if the pore pressure rises too high, it pushes the particle apart. And so looking at the effective stress equation, when the pore water rises, it causes a reduction in the effective stress. So let's look at behavior under increasing pore water pressure. So we have 3 series of diagram here that visually explains how effective stress is lost. So in the middle image, the white arrows represent the strong contact forces between the soil grains when the pore water pressure is low. So as pore water rises, those intergranular contact forces are gradually reduced. And so if the water pressure gets too high, the contact forces vanish, and that causes the solid particles to become loosely suspended like a fluid. And this is the moment that liquefaction happens. And so in the middle picture, we see this blue column here. This is indicative that the pore water pressure, the pore water is very low. So as the pore water rises, that we see in the right image, we see an increase in the level of the pore water. And so that means that the contact particles are being broken down, and so liquefaction happens. So this slide addresses why paste fill is susceptible to liquefaction and what type of event can trigger this failure. So paste fill is considered highly susceptible to liquefaction, and this is because paste fill material just retain the water used during the transportation and placement, and this means that the fill mass is nearly saturated. And also paste fill contains high proportion of fine solids, and this results in the material having very low permeability, which critically prevents excess water pressure from dissipating quickly when the material is stressed. And liquefaction can be initiated by 2 categories of loading. The first one is the dynamic loading, which is characterized by sudden rapid disturbances like blasting, rock burst, seismic event. And we also have static loading, which is characterized by the gradual stress buildup, such as from the weight of overlying rock or slow rock mass movement. So we have 2 material types under different loading conditions that we want to use to explain this liquefaction. So first we have loose soil, we have dense soil. And for the loose soil, we have the monotonic loading and then the cyclic loading. So for the loose soil, the material is contractive, which means that it tends to decrease in volume when sheared. So under monotonic loading, the material flows and the shear stress drops sharply to the undrained steady state shear strength, which is the SUS. And once the shear stress drops to this point, it indicates flow failure. And under cyclic loading, the pore pressures increase until the shear resistance drops to SUS, which is the undrained steady state shear strength. And that results in complete liquefaction. Now for dense soil, the material is generally dilative, which means that it tends to increase in volume when sheared. So under monotonic loading of the dense soil, the shear strength reaches a peak, that is the SUP, and then reduce slightly to the SUS, but it remains high. And under cyclic loading, the pore pressure increases, but the tendency towards deformation is resisted by the soil mass stiffening and increasing shear stress. So looking at some core mechanics of liquefaction, the first one is the effective stress principle, which is given by this equation. We also have the undrained shear strength, which can be calculated based on the general Mohr-Coulomb failure criterion, which is also illustrated illustrated here. And the ECS is generally the most common method to measure the strength of paste fill. So the relationship between the ECS measured and the undrained shear strength parameters is also illustrated in this equation. And the last one, we have the pore pressure coefficient. So the change in pore pressure resulting from an increase in isotropic stress is calculated using the Kapteyn's pore pressure coefficient, which is also given by this equation. And this relation is very important because a material must have a B value of 0.95 or above to be confidently considered saturated. This slide talks about liquefaction evaluation procedures, and this brings us to a concept called the steady state of deformation. That's the SSD concept. And this SSD concept is the primary framework that is used to evaluate liquefaction risk. And it performs a stability analysis by comparing the shear force exerted on the material against the minimum strength the material can sustain internally. And that brings us to the factor of safety. So the stability analysis is quantified by the factor of safety FL, which is calculated using the ratio of the undrained steady state shear strength at steady state to the shear stress required to maintain static equilibrium. So SUS, the ratio of SUS to D. And then the relative density. So the material's physical resistance is linked to the relative density, which is the measure of the particle packing density within the deposit. And the relative density is calculated by using this equation right here. Yeah. So E is the in situ void ratio, while E max and E min are the maximum and minimum possible void ratios, respectively. So generally, materials with low relative density, below 30%, are considered highly prone to liquefaction. Slide talks about the prevention and mitigation of liquefaction. The first one is through cementation, as when cement is added to a paste fill generates cohesion. Also, we can prevent that through required strength criterion, which is the UCS. And so generally speaking, a UCS value of 100 kPa is generally considered sufficient to prevent liquefaction. Also, mitigation through saturation control. So placing paste backfill in an unsaturated state is considered the most reliable way to minimize liquefaction risk because it prevents high pore pressure from building up. And also, as I said previously, a material must have a pore pressure coefficient of 0.9 or above to be considered saturated. So in the next few slides, we'll be looking at a concept called arching and load transfer. So what exactly is arching? Arching is just a mechanism where differential stresses will transfer the weight of the backfill onto more stiffer adjacent rock walls. And this usually happens because the backfill is not a rigid block. It yields. And so as the backfill yields, it settles and moves relative to the stable rock wall. And this movement generates shear resistance at the interface between the rock and the backfill. And so this interaction is very crucial because it effectively reduces the pressure within the fill mass itself, meaning the fill doesn't have to support its own full weight. And so if you look at the diagram on the left, it's just showing a schematic of how this backfill presents confinement at the boundary of an excavation. And this confinement assists in mobilizing shear strength along the existing joint, and this helps to arrest any potential propagation of failure. Now to the picture on the right is showing a visual proof of this. arching mechanism. And so in the diagram, we see the dotted pink line and we have the solid pink line. The dotted pink line represents the geostatic vertical stress, and the solid line represents the fully arched vertical stress. Now you notice how the solid line is significantly lower than the dotted line. Yeah, so that gap between the solid and the broken line, the gap in between represents the load that has been successfully transferred to the rock walls. So having established the concept, let's move into the physics that describes it. And so this brings us to the fundamentals of this arching theory. So the core principle here is that the arching transfers the majority of the overburden weight away from the backfill and onto the rock wall. And so to quantify this, we use models like the simple arching, which originally was proposed by Matson in 1930, and later modified versions. So let's look at this diagram here, which is representing the free body of forces acting on an isolated layer. So this diagram is the foundation of the analytical model of arching. It shows a thin, isolated horizontal layer of the backfill with height dh, and this is contained within the stope of width b. So we see the weight of the material in the layer W. Yeah, this is W. And we also see the vertical stress V, which is acting down on the layer, and the slightly increased vertical stress V plus dV acting below it. So most importantly, we see the shearing force S on both sides. That's, yeah, acting along the sides where the fill contains the rock. And these forces are the frictional resistance generated by the walls. And so the principle here is that the vertical equilibrium of this small element requires the weight W, and the forces acting vertically must be balanced by the shear resistance S transferred to the sides. And so this balance of forces is the foundation for the derived arching equation, which is represented right here. And so in the arching equation, the term sigma Vh is the vertical stress experienced at a specific depth. We have gamma, which is the unit weight or the density of the fill. B is the width of the stope. H is the depth below the fill surface. Delta is the effective frictional angle between the rock walls and the backfill material. And K is the coefficient of lateral air pressure. So this equation shows that the vertical stress, which is the sigma Vh, is related to the initial density gamma, but is rapidly reduced because of the exponent equation is rapidly reduced based on the geometry B and the material's ability to transfer load. Yeah, so full arching occurs when the shear strength along the walls is completely mobilized. So let's look at some real world consequences. So the most important takeaway here is that arching isn't just a minor effect, it creates a substantial reduction in vertical stress. And so let's analyze the figures on this slide. On top we have two figures, one in plan view and the other in oblique view. And these figures illustrate the spatial distribution of vertical stress across a horizontal plane of a fully confined stope. Now looking at the plan view figure, the contour lines map areas of equal vertical stress. And so the major trend is that the stress is highest in the center of the stope. So we can see that in the center we have the stresses reaching around 160 kPa, and stress is lowest near the confining walls and especially in the corners. So we can see that in the corners the stresses are around 60 to 70 kPa. And looking at the oblique view, this is showing like a dome-like shape of the developed arc profile. And the reduction in stress, it just demonstrates that arching transfer some vertical load to the supporting walls. Now to the graph here, this is a experimental test that was conducted, and I wanted to show that in this graph we have on the x-axis the vertical normal stress, and so this plot is just tracking the vertical normal stress down the center axis of the stope. So the diagonal line is representing the hydrostatic stress, which assumes no action, and the curved line is showing the actual vertical stresses down the arching material. And so looking at the trends, we see that arching for the arching material is substantially lower than the hydrostatic stress profile. And we can see that the stress increases briefly near the top and bottom of the arching profile. But in the middle part, we see that the trend is fairly constant. And so this constant stress proves that the entire weight of the overlying fill in the central column is successfully transferred to the walls by shear. So on this slide, we want to look at what controls how strong an arch can be. The most important takeaway here is that arching is predominantly a geometrical effect rather than a material one. So the critical factor that determines the maximum stress isn't the strength of the cement, but the minimum base width, which is the minimum base dimension, which is a W. So to make things shorter, narrower stoves arch better than wider stoves. Also, if you look at the wireframe images that we have on top, it's just showing comparing a 2D arch to a 3D arch. The 2D is like a tunnel, the 3D is shaped like a dome. So whilst the 3D is stronger, a 2D is still very efficient, and it actually retains about 85% of the effectiveness of a full 3D arch. So now let's look at the contact interface. With this, we want to show that the quality of the walls matters here. And so looking at the graph at the bottom, we have a pink line, which is representing the rock fill interface. We have a blue line, which is representing the fill interface. And we can see that the pink line stays higher, meaning it has better arching potential. So generally rock walls are stiff and they provide excellent support. However, when you are filling against other backfill, the fill walls, it provides only about 33% to 66% of the arching potential you get from actual solid rock. And so we are saying that rocks provide better arching potential. That when you backfill against rock, you get higher arching potential than when you backfill against another backfill. So let's look at some analytical modeling and design tools. And we will start with the analytical methods. So for standard narrow stopes, we still rely on the fundamental simple arching theorem. But we need to know that mining isn't always simple. Sometimes we have complex scenarios like filling next to another fill stop. And so in that case, we use a modified simple arching equation. And This method is crucial because it uses a specific ratio that is called the effective wall area, R, and this ratio accounts for the different interface types that we see. So for more complex geometries, simple equations aren't enough. So we use numerical modeling tools like Flat 3D. And these simulations just allow us to model the entire extraction and filling sequence over time. And that kind of validates exactly how the stress arch develops. So let's look at the user interface image on the top right. This is what the design engineer actually sees. So we have input parameters like the stop width, the height, fill density, and outputs like the model calculates the maximum vertical stress. So in this diagram, we see that as 281 kilopascal. And it then tells us the optimal cement content, which is highlighted in red as 3%. And so it's just telling us the optimal cement content that is required to ensure our strength meets the that of the stress, as in the UCS is greater than or equal to the sigma Vmax. So in the next few slides, we will be talking about barricades and the instability issues related with barricades. So far, we've talked about material science, but now we are talking about safety. Because if the backfill fails inside the stop, it's an operational problem. But if the barricade fails, the material will just flood into the active tunnels where people are working. And so this section basically explores why these failures happen and how to prevent them. So a barricade is simply a retaining wall like structure that is built at the bottom of the stop just to keep the wet paste inside. So when we first pour the paste, it acts like a liquid, and this liquid creates hydraulic pressure. And so this tiny wall, the barricade, has to hold back thousands of tons of this liquid mud. So the main job is to make sure that it holds the hydraulic pressure that is being exerted on the wall as a result of the liquid paste. And so if we get the calculations wrong, the results is going to be catastrophic. Yeah. And so this slide mentions the Bronzewing mine disaster in 2000. And in that case, a barricade burst and thousands of tons of mud flooded the mine, and it led to killing of people, and equipment were destroyed as well. So it's very important to ensure the stability of the barricade. And historically, miners just built these walls based on their gut feelings or like past experience. But currently, people are conducting research and modern engineering also coming into place just so we can replace the gut feeling with calculated physics just so we could ensure that a disaster does not happen. So how do we calculate the exact force hitting that barricade? The primary load we are fighting is the lateral hydraulic pressure, and this is the wet paste pushing sideways against the wall. So if backfill were water, calculating it would be easy because pressure will just increase with depth, but backfill has friction. And so this brings us to the critical role of arching. And as I mentioned earlier, the rock walls, they just grab the fill and that holds up some of its weight, like we explained in the previous slide, and this kind of reduces the pressure reaching the bottom. So to quantify this, we use the equation in the middle, which is sigma h prime equals k naught times sigma v prime. So sigma v prime is the vertical weight of the fill. Sigma h prime is the horizontal push against the barricade. And K naught is the coefficient of earth pressure. And the formula below that, which is K naught is equal to 1 minus sin phi prime. It just shows us that this ratio depends entirely on the friction angle of phi prime. So the rougher the material, that means rougher materials have high friction. And so the rougher the material, the lower the K naught and the safer the barricade. This slide talks about some factors that influence the instability and failure mode, and the most important variable we control is the failing rate. So let's look at the graph. On the right, it plots pressure on the barricade on the y-axis and the failing height on the x-axis. And each color line represents different failing rates. So look at the top red line. This represents a very fast failing rate at 2.0 meters per hour. The pressure skyrockets to over 500 kPa. Yeah. So if we track the pressure on the y-axis, we see that it's a little over 500 kPa. While looking at, let's compare that to the bottom blue line. This is a very slow rate at 0.3 meters per hour, and the pressure stays extremely low, barely touching 50 kPa. Yeah. So why this difference? This is showing that when we fill slowly, we give the water time to drain and the cement time to start hardening. But if we fill too fast, that means the material stays liquid and that creates massive hydraulic pressure. Now look at the flag 3D model on the left. This simulation is just showing the stress concentration on the barricade. So you can see red, yellow zones right at the bottom corner. And this illustrates what we call the punching failure. And only the stress, it means that the stress doesn't push the whole wall over. It just concentrates at the base and tries to punch a hole right through the barricade. The key strategy for mitigation involves ensuring that the backfill develops high early strength. And so this gain in strength at the early stage just minimizes the total time the barricade must contain the hydraulic load, and that will reduce the chance of failure. This point is understanding the critical height HC. So if you look at the graph at the top, we are calculating the critical height. So as we fill the stop, the pressure rises, but at a certain height, which is the critical height, action kicks in. And so the rock walls take the load and the pressure on the barricade plateaus. That means it stops rising. So our goal is to manage the failing rate so we can reach the safety plateau without busting the wall first. So this graph has the critical height on the y-axis and the failing rate on the x-axis. And so this graph is telling us that if you fail faster, as in if you move right on the x-axis like that, that means the safety plateau would happen much later on the y-axis. So the further we go on the x-axis, the higher the value of the critical height will be on the y-axis. So this is saying that it's better to fail to have a lower failing rate in order to achieve a much lower critical height value. This brings us to the design implication of backfill geomechanics. And the first one is the cost-effective stability. So this is the bottom line. Cement is the single most expensive operating cost in backfill. And so if we are able to accurately characterize the material, we can optimize the mix parameters. Because reducing the cement content from just 3.5 to 3 might sound small, but over a year, that small reduction can save the mine millions of dollars while still maintaining stability. The second point is incorporating arching as a tool. So we don't just hope for arching, we have to design for it. And by understanding the geometry, we can shape our stopes to maximize the natural load transfer to the walls. Also predicting stress using advanced geomechanical models. So now we are not just doing guesswork, we are moving away from that. We are using analytical methods to predict exactly how much stress to feel the backfill will face. So to wrap up the technical analysis, we must acknowledge that our industry still faces some significant knowledge gaps. And so despite the advanced models that I've shown, we still haven't solved everything. So the first one is the barricade loading uncertainty. We still struggle to predict exactly how much horizontal force will hit the barricade. Also, second is the lab to field gap. And as I highlighted earlier, just scaling up a 10 centimeter lab sample to 100-meter stope is difficult. We need to better calibrate our methods just so we could make lab data to match the reality. That is the stability criteria. So we need to refine our definition of stable. And just because a stope stands up doesn't mean it's optimized. We need more precise numbers on exactly when it is safe to blast the next panel. The fourth is anomalous behavior, because sometimes the chemistry does unexpected things underground. We could have groundwater salinity or temperature spikes that can cause the paste to behave in ways that standard textbooks cannot predict. And finally, standardization. Right now, every mine does characterization differently. The industry needs a unified standard for testing backfill, similar to how we have standards for concrete in civil engineering. These are some references. So thank you for taking the time to go through this entire presentation.